Greetings! This presentation is a brief summary of oxidation reduction and all of the related concepts we use to calculate various parameters in the environmental sciences from the presence of oxidized and reduced forms of matter. The first concept I want to remind you about, which you learned in one or another prior chemistry class, is oxidation state. Oxidation state is basically bookkeeping for electron transfer. It is a measure of the charge on an atom in any chemical form. It is the atomic number minus the number of orbital electrons a chemical species contains. So for instance, in the simplest case for a monatomic species, it is just equal to the ionic charge, such as in the case of iron +3, the oxidation state is +3. For chlorine -1, the oxidation state is -1. If we were to look at helium gas or argon gas, which don't have a charge but are monatomic species, in those cases the oxidation state would be 0. Okay, so now I want to do a little bit more review of how we assign oxidation states in molecules or compound ions. And it's calculated using some simple rules. And I'm going to go through those rules now. So the first rule is that the algebraic sum of the oxidation states of individual atoms in a compound equals the charge on that compound. Any atom bonded to itself in a pure covalent bond and only bonded to itself is given an oxidation state of 0. So for instance, nitrogen, oxygen, and hydrogen atoms in the molecules O2, N2, and H2, these are all 0. The oxidation state of oxygen is given a -2 value as kind of a master variable in all compounds except molecular oxygen, as noted above, and peroxide molecules, which have the form H2O2, Na2O2, and as we will discuss later in the semester, there are many other kinds of peroxide radicals in organic chemistry that take the same form. In peroxides, they're given a different value. The oxidation state of hydrogen is always +1 in all compounds except those where there's a metal-hydrogen bond, in which case we assign hydrogen a -1 and call it a hydride. In compounds containing hydrogen and oxygen, lacking hydrogen and oxygen but containing halogens, except in case B, which are halogens bound to themselves, such as chlorine 2, chlorine gas, in which case chlorine would be assigned to 0. In all other cases, the halogen is assigned an oxidation state of -1. This only applies when we don't have oxygen. There are cases where a halogen can be bound to oxygen and the halogen doesn't have a charge of -1. So rule F really only works as a rule of thumb in molecules that have halogens and don't have hydrogen or oxygen. In almost all cases, you can assume that alkali metals, which is the first column of the periodic chart on the left-hand side, and alkaline earths, which is the second column on the left-hand side, have oxidation states of +1 and +2 respectively. This is only superseded by some of the above rules, which are pretty rare cases, so we're not going to worry about them. Okay, so let's see how this works in molecules. I want to emphasize that oxidation state is a bookkeeping method, so it's an approximation of the actual charge distribution in molecules. Sometimes it's a really good approximation, such as when we have strongly ionic bonds and electrons are being transferred. And sometimes they're not such a good approximation, such as in covalently bonded molecules. So here's an example for the molecule sodium chloride, which we all recognize as table salt, or the mineral halite. It's an ionic compound. And using the rules I just went through, chloride would be given a charge of -1, and sodium would be given a charge of +1. And this would allow the molecule charge to be 0. The bond is highly ionic, so oxidation states are realistic. However, as I just noted above, in covalent molecules, when we assign oxidation states, they're a less precise measure of the reality of electron density around the atoms. Nevertheless, we use the same bookkeeping methods to help understand electron flow in electron transfer chemical reactions. So let's look at another molecule. This is a covalently bonded molecule of nitrogen and oxygen, one of the many forms of the nitrogen oxides that exist. This is a relatively reduced one, NO. The oxidation state rules tell us that we give oxygen a -2 value first, and therefore nitrogen is given a value of +2. So if we add those things up together, we get a molecule that has a 0 charge to it, because the +2 and the -2 cancel each other out. And the oxidation state assignments imply that we have transferred 2 electrons from nitrogen to oxygen. However, this is a very covalent bond. These are elements that sit right next to each other in the periodic chart, and they're sharing those electrons. So the donation that's implied by the oxidation state is not really taking place. Nevertheless, we use this convention to help understand the flow of electrons in what we call REDOX, which is a shorthand for reduction oxidation chemical reactions. So we can use redox and the bookkeeping methods that we just used to understand this reaction of NO plus the compound ion ClO minus in chemical equilibrium with NO2 and chloride ions Cl minus. We can apply all the bookkeeping methods, and I've done that in the table below, which shows you the oxidation state of oxygen, nitrogen, and chloride on both sides of the chemical equation. And if you look through it, you will see that there has been a change in, for instance, the oxidation state of the chlorine, as well as the oxidation state of the nitrogen. So we can further quantify this by something that we call a half reaction. Half reactions are used in the case when we have electron transfer between products and reactants, and the only way we can guarantee that we know that there has been electron transfer is to look at the oxidation states of every chemical element in every molecule on both sides of reaction to see if they have changed or stayed the same. If they have changed, then we are transferring electrons from one thing to another, and we can think about the half reactions as being 1/2 of the chemical reaction is an oxidation, and 1/2 of the chemical reaction is a reduction. And in chemistry, we talk about oxidation as the process of losing an electron, and reduction as the process of gaining an electron. There are all sorts of different mnemonics out there to remember this. The one I was taught as a student is that Leo the lion goes grr, which stands for lose an electron is oxidation and gain an electron is reduction. You can always apply this simple memory trick and looking at the bookkeeping of the various oxidation states to decide which chemicals are being oxidized and which chemicals are being reduced. In fact, I was a chemistry major as an undergrad, so I actually learned that Leoa, the lioness, goes grrk. And the only difference in that slightly different way of saying it is that you lose an electron, which is oxidation at the anode of a battery, and gaining electrons is reduction at the cathode of a battery. So let's decompose the chemical reaction I did the bookkeeping for into half reactions. So I've written out 2 half reactions, one where NO goes to NO2 plus 2 electrons, and the other one where ClO plus 2 electrons goes to Cl minus. You can see from those 2 half reactions that one of them, the first one, is a case where something is losing electrons, and the second half reaction is a case where something is gaining electrons. Okay? So those two reactions that I wrote, which just come straight from the chemical reaction above, and which can be algebraically added back to it, are balanced when they're written together in a full-form chemical reaction, but they're not balanced as half reactions. We can see that they're balanced for electron flow, but they're not balanced for matter and charge. So we need to add or subtract various components of water or hydrogen ions or hydroxide ions to help make a half reaction that is balanced for charge and material. And I've shown you those at the bottom, right, where we've added in water and hydrogen ions. You could have also written these equations slightly differently, where you add in water and hydroxide ions to also balance it out, but this is the simplest reaction, and these are the ones that you would find in a table. And I can highlight here which reaction is the LEO and which reaction is the GER. When added back together, the added water and the hydrogen ions that we put into material balance and charge balance, the half reactions, drop back out, and we end up with a chemical reaction that in net looks like the reaction at the top of this slide. Now, if you don't remember any of the details about how to algebraically manipulate chemical reactions together or half reactions, I suggest you look in the chemistry review pack that I alerted you to at the beginning of the semester, because I discussed that there. Okay, so the next thing I want to mention is the Nernst equation. You probably remember this equation at some point for solving problems about electron flow in batteries, or about whether or not a mixture of chemicals at some concentration would react with each other to produce a flow of electrons and to change the oxidation states of some of the chemicals that are present. So the Nernst equation is written out as delta E, which is the reduction potential or the electromotive force, equals delta E naught, which is the standard state value, plus 0.059 over N times the log of Q at 298 K. At chemical equilibrium, where we have an equilibrium assemblage of materials, this equation, I should say, reduces down to delta E naught equals minus 0.059 over N log K, where K is the equilibrium constant. Now remember, Q, which is the reaction coefficient, is just the sum of the products over the sum of the reactants, and at equilibrium, Q is K, the equilibrium constant. So they both take the same form, they look the same, but K is the special case of Q where we have the right mixture of product and reactants to know that we are at chemical equilibrium. And I apologize for the slight offset in the formatting on this slide, but hopefully you can see that, for instance, in the green line where I've written out delta E naught equals minus 0.059 over N times log K, that bracket NO2 times bracket chloride should sit right over bracket NO times bracket ClO minus, which is the sum of the products over the sum of the reactants. Okay. The other notes on here, just to point out that that little degree sign, or the 0, that denotes the standard state. Just to jog your memory, the standard state is 25 degrees C and 1 atmosphere pressure. 25 degrees C is 298 Kelvin. And N in this case is a number of electrons transferred. So if you go back to the prior half reaction that we talked about, in that case, N would be 2 because 2 electrons were transferred. Here's a couple of other useful thermodynamic relationships that you've probably learned in the past. I'm not going to expect you to memorize these things. You can always refer to them. You can find them in almost any textbook. But I just wanted to remind you that the delta E, this reduction potential, is directly related to the Gibbs free energy. And if you recall, the Gibbs free energy, which we highlight as delta G, tells us about the ability of mixtures of chemicals to react or not react, and what proportion we will have at chemical equilibrium as a function of two components, the enthalpy and the entropy. I haven't bothered to give you the relationship between delta G, delta H, and delta S on this slide, but it's just something to remind yourself of. So delta G, the Gibbs free energy, is just NF delta E, N being the number of electrons transferred, and F being the Faraday constant. Now our textbook uses a capital F, and I'm using this lowercase f for the Faraday constant, but in any event, you can look that up in a textbook, and it has different units depending on which system you're using. For instance, I've given you F for kilocalories, but there's another value of F if we're measuring things in joules. You'll also see R in these equations, which is the universal gas constant. You want to make sure that you're using the value of R, which can also be given in calories or in joules or in ergs, that is consistent with the value of F that you're using. They both need to be in the same units. You can see some of the other abbreviations that I've shown you down there in the bottom. The other note I wanted to point out is that when we put P, lowercase p, in front of something, that's just a shorthand way of saying we're taking the minus log of that. So P of parentheses x is the minus log of x. The most common place you have seen P is in the form of pH, which is the minus log of the hydrogen ion concentration. We will learn in lecture that PE is the minus log of the electron concentration. I want to get ahead of ourselves. Just for now, know that when we have PE, we're really talking about the minus log of the concentration of something. So you can see some of the other equations that fall out from just algebraic manipulations of the Nernst equation or the equation in the top box, and they're given below. And I want to highlight the bottom two boxes on this slide, which show us that when we do the operator PE, it is simply a series of constants times the E, the reduction potential. The way we translate between the two is F over 2.3 RT, T being the temperature, R being the universal gas constant. And at 25 degrees C, which is 298 K, that little thing, that series of constants, F over 2.3 RT, collapses down to 0.059. So that you can see the relationship. For instance, PE equals E over 0.059. They're just offset from each other by a constant. Now, of course, if we were doing a calculation for a different temperature, like 0 degrees C, or 50 degrees C, or 100 degrees C, we would have to put in a different value of T, and that 0.059 isn't going to hold anymore. But it's a pretty simple transformation to do that calculation. So the way we use the Nernst equation, which is in its most shorthand form at chemical equilibrium, is delta E naught equals minus 0.059 over N times log of K, is by looking up values of E naught for half reactions and adding them together to get an E naught of the reaction. Rxn is my shorthand for reaction. And these you can find in tables. And we use these things that are calculated relative to something called the standard hydrogen electrode, sometimes abbreviated as SHE. Okay? And the standard hydrogen electrode is just, like I say, a standard that we use, which says that the half reaction between hydrogen ions, H+, and hydrogen gas, H2, which is a reduction to go from H+ to H2, we assign that a value of 0. And then we look at all other half reactions relative to that, so that if they flow electrons or don't flow electrons in a relative sense relative to that, they will have an E naught value which is negative or positive relative to that one.